there are two algorithms that you should know. That support vector machine and maybe logistic regression, softmax. So that will take a little bit of time. So I'm going to teach those after the midterm exam. Okay? And those things really require you to do some programming. So I want to see how I do today, and then I want to talk about regression a little bit. Regression. And so I have sort of modified my the scheduling. Okay? I want to let you know. I've modified the scheduling a little bit, and I want to give you the reason why I'm doing this. Okay, so before I start, let me just do we have the updated PCA?
오늘이요?
Oh,
아니면 어제 기준으로 업데이트가
okay, so I just want to just say that. Okay, so I was looking at this, first of all, very easy one, the Chow-Liu algorithm.
차를
Oh?
업데이트
Okay, so I think so. Let's look at this. So, if you remember, Chow-Liu algorithm was if you are given the data, okay, you want to generate a graph based on that data, okay? And the Chow-Liu algorithm provides tree-based algorithm as an output. And I was going through this example. I had to calculate the mutual information between all the attributes. And then I ranked them. And I had this thing as I was going. So I ranked it 2 and 3. That was the mutual information. 1 and 5. So the next one was 1 and 5. Oops. 1 and 5. And then I had to link up 1 and 2. And I had a link from 1 and 3. So what I was trying to say was there was a typo here. This was 3 and this was supposed to be 2. Okay? So that typo has been modified. Okay? So essentially what you do is you find out all the mutual information, you rank it, and then you just link up. And the only thing that you have to remember as you link up, is this a tree? If it's not a tree, then you skip. Okay? It's simple as that. Very, very simple algorithm. Okay? Chow and Liu. And Chow and Liu also Chow and Liu maximizes the sum mutual information. Okay? Maximizes the sum mutual information in a graph. Okay? And that is like taking the maximum, you're maximizing the log likelihood. You're maximizing the log likelihood. Okay? You want to find a graph, a tree graph, that maximizes the log likelihood. Which tree graph would do this? And it would lead to maximizing the sum mutual information. Okay? That's what you're getting at. And I forgot to say also this. If there are k nodes, so how many nodes did we have here in this case? Was 5, right? If there are k nodes, that leads. Do you know what's the possible tree graph you can get? The number of tree graphs that you can get. from k nodes. What? Wow, that's great. Yes. That's the number of trees that you can get from the graph. The proof is not really simple, but oh, that's wow. Is this a small number? No. This is a large number. If you have lots of nodes. Of the k to the k minus 2 tree graphs that you can get, Chow and Liu gives you the highest log likelihood. And it's like maximizing the mutual information, the sum mutual information. Okay. And also of them, it minimizes the KL divergence between the true probability distribution and the distribution that this graph gives you. This algorithm was proposed 1968. Fantastic algorithm. So I've modified those slides on that, okay? Wow. You know, each year I'm really surprised at the ability of some of these students to. Okay. This is probabilistic PCA that I talked about yesterday. So, in probabilistic PCA, looks like this. You have a high dimensional data, low dimensional data. Okay, it's coming from some low dimensional data, and everything is Gaussian here. Everything. But your assumption here is that the latent variable are Gaussian, zero mean and unit variance, each one. And also there is a Gaussian noise associated with this link. I hope you remember this equation, how that relates. That's Gaussian. So the marginal probability of this is Gaussian. So the marginal probability of this is Gaussian. This is Gaussian. Okay. The conditional probabilities are all Gaussian. And I said something not correct. Someone pointed this out, which was very good. And I think is it possible that I can write this? They are independent. Oh, the labels are independent. No, I think I said. I might have mistaken. This is certainly not true, right? Is this true? That's not true, right? We're assuming that the data, these dimensions are correlated, right? What about if I want to make it independent, what do I do? Yes, I need to have given x and 1 through x. What was it? So there is notation. This thing has to be updated. I don't think this was updated. This has to be xn1 to xnq. There has to be n, please. There has to be n there. Okay? So, how would I write the conditional independence on this one? Is this correct? Is this right? Once again?
R of x.
Yes, very good. All of that. Very good. Okay, I don't think someone told me that I said, I didn't say this, so I will make sure to do this. I'm going to upload a paper, one or two papers regarding some of this. Oh, and now another thing, there's some typos here that we check this. S was the sample covariance. Okay, the sample covariance was defined. I think I defined. What was it? What was it? Y that. Was it Y? Yes. Y. N. Let's say Y I. This is vector Y I minus. I'm just going to put Y hat. This is the average value of Y. Okay. This is a vector. Transpose. How can I do that? Okay, that's the sample covariance. Covariance. So this is what dimensional vector is that? Oh, wait, sorry, I left something out. Oh God. Sorry about this. It's S, n over 1, and summation I equal 1 through n. I probably didn't do this. Okay? This is sample covariance. What dimension is this? What dimension is this? This is d-dimensional vector, column vector. This is what? D-dimensional row vector. This one gives you a matrix, d by d. What's the rank of this? What's the rank of this? Please. What's the rank of this? It's a vector. Then I take the outer dot product. What's the rank of this one? It's rank 1. Oh, come on. You take an outer dot product, so that's a matrix, right? So this is rank, each one is rank 1. And this is d by d. Okay? And I sum up n of them. I sum up n of them, and I take the average. What is the rank of that? What is the rank of S? What? I have a whole bunch of rank 1s. And I add them up. They're different. I add them up. What's the rank of S? T? Where's T? No. Oh. If n is greater than d. If big N is larger than d. Okay? If big N is larger than d, then the rank is d. Because each one of them is. Okay? Right. If it's not, then what is it? Then it's n, right? Okay, so I want to make that sure. Okay, I hope everyone understands that. That's very good. Let's assume, I don't know if you've heard of SVD decomposition. SVD. Who has heard of SVD? Raise your hand. No. Who has not? Okay. Have not. Very good. Thank you. Thank you. So, let's assume this S has D rank. How many eigenvalues will it have? How many eigenvectors will it have? And I'm going to assume that they are all, the vectors are all different. How many? D, good. U I equals lambda UI. Like that, right? This is eigen. That's the definition of eigenvector, right? And then I have I equals 1 through D. What's the property of each of these UIs? What is the property of the U's?
They are independent.
They are orthogonal, okay? Orthogonal. So what I can write, what does orthogonal mean? UI perpendicular to UJ. Let me just write it this way. Okay, or I take the inner dot product IJ and it becomes a delta IJ. Everyone understand this? This is 6th grade math. Huh? No? Okay. So, I'm going to put all of them together. So, can I write this thing like this then? Let's see if we can do this, if I can do this. Something, I'll just put V here. Can I write it like this? Can I do that? Can I do this? Can I write it like this? This to that. How?
If you multiply the first two matrices, you get columns with lambda I ui, and then you make the last matrix as the inverse.
Very good. Very good. Okay, so you can, okay, I'm not should know this is, you can write it like this in matrix form. These UIs are the eigenvectors, eigenvalues. Okay? So, and that's what SVD is, basically. Okay, so S can be written like that, where this is D-dimensional vector, and I have D of them. They're orthogonal. The lambda, there's 0, 0 here. it turns out, okay, if the covariance is, what kind of property does it have? It's symmetric. It's semi-positive definite. Eigenvalues are greater than 0, right? Now, this is something that I will not go through, and I hope you will understand. If the y's are coming from Q low dimensional data, and there is no noise. Let's say there's no noise added. So meaning, if epsilon was 0, this one is 0. Okay? And mu is equal, let's assume mu is equal to 0. Okay? What would, and it was d-dimensional, somehow it was d-dimensional. Huh? What can you say about the eigenvalues? So it's this. S is equal to Wx. And this is, oh, not S, sorry, Y. This is coming from, this is, what is it? This is Q by 1. Low dimensional Q. What is this? D-dimensional. What can you say about the eigenvalues? Some of the eigenvalues. You understand what I'm saying? There's no noise now. Okay, I'll just erase some of these things. So I just want you to focus on this one. Y is equal to Wx. This is Q by 1. This is, what is it? D by 1. And S was defined this way.
Some of the values are 0.
How many?
Q minus ID minus Q.
Yes! Those will be zeros. Everyone understand that? Lambda Q up to lambda Q. That's a very good important fact. So this lambda, I'll try to fix this thing up. Lambda Q, lambda. After this, lambda Q, this is lambda Q. For this, that would be 0. That'll be 0. But in our model, what are we doing? In the probabilistic PCA, we assume that there is epsilon. That's noise. Epsilon, and I'm assuming that epsilon is, in the probabilistic PCA, it's 0 and sigma squared I. Then what's going to happen? Then those ones should be what? What?
Sigma squared.
Sigma squared. And the other ones will be added with sigma squared. That's a very important fact to know. I'm going to put up a paper regarding probabilistic PCA. Okay, there are some nice math and some, very interesting graph model, and it's a nice exercise for you to play around with. Okay, so this is what I'm going to do. I haven't gone through each detail, and you are not satisfied. Well, but I don't want to spend too much time on this one. Okay, but I already did. So that's good. Today I move on to another topic. So I'll put out the reference paper. Today I'm going to talk about this algorithm called expectation maximization. EM algorithm. It's an old algorithm, but it's something that you should know. Okay? Why? Because in our setting, we want to do machine learning. So we have data. And our task is generally to come up with a model from data to the label. Right? The function. We want to find the function. And the function is what? Parameterized by what? Theta. Right? And this function, this class of function, what do we call this function? Class of function? What do we call it? Space. Very good. Hypothesis space. Now, from the hypothesis space, we pick a model, and what do we have to do? We have to determine what the theta is. Right? That leads to parameter estimation. What technique what's the criteria or the loss function or to get our theta that we learned? Can you tell me? How do we get theta? There are probably many ways to get theta. What was one of them? Very good. Maximum likelihood. Another one was maximum a posteriori. Posterior mean. Or if we have a loss function, what's the technique that we get? No. Bayesian estimation. It's based on the loss function. A whole bunch of them. Right? But the method that lots of people use is maximum likelihood, or maximum a posteriori. How do we solve maximum likelihood? What is likelihood? We have to first formulate what is likelihood. What is likelihood? Yes, very good. Probability, so you should look at probability of the whole observation. Then you have to use your IID assumptions to split that up. Or maybe there's a graph based on that. Right? You get it's a probability of the observation. Right? Maybe it's based on some graph, maybe it's not, but you have to get your likelihood. Then how do you do it? How do you want to maximize the likelihood? How do you maximize the likelihood? What's the technique? You mentioned one of them, but or log likelihood. I know, but how do you solve that log? What do? You want to maximize the log likelihood. What is the one way to maximize the log likelihood? with respect to the parameter? It maybe it's easy question. You take the derivative and set it equal to 0, and you solve that equation, right? What happens if that is not easily solvable? I take the derivative and set it equal to 0, and I should be able to arrange it so that theta equals what? What's on the other side? What should be on the other side? Theta equal what on the other side? What's a function of what?
The observations.
Huh? Function of what?
Observation.
All the observation. Very good. You should be able to get it. Theta equals some function. Then you can get it. But what happens if it's not? Then there is a technique called expectation maximization. Not only for log likelihood, but for other things as well. That's one technique. And he mentioned another technique, which was, you mentioned it, gradient descent. Okay? So many algorithms these days are, you get your parameter by gradient descent. Okay? But today I'm going to talk about expectation maximization. Okay? Does everyone understand the setting? What we are doing right now all the way? Oh. So I'm going to do this by, okay, so here it is, I'm going to go through this lecture by example. First of all, okay, so, likelihood. I want to get the parameter of the likelihood. What happens if you're given data and label? What should you look at? This is the, if you're given data and label, what should I be looking at? Not the likelihood, but what? I got data and label. Here is only data. What should I be looking at if I have data and label? No. Conditional likelihood. Remember? This one. I should be looking at, if I have label, y1 through yn given x1 through xn. Given. This is what I should be thinking about. This is when you have data and label. This is only when data. Right? I mentioned this. So if they're independent, you could do that, or I could do the log and do that. How do I maximize it? Oh, I take the derivative of this, right? And set it equal to 0. I could be looking at the maximum a posteriori. So it's data given like that, which I can use Bayes' rule to do that. This bottom thing, what do we call this bottom thing? It's called evidence. It has a name. Then you do that. So look at the maximum likelihood. Maximum there's a log here. I didn't put a log. Oh. What would be the difference between that and this one? Maximum a posteriori estimate? Maximum likelihood estimate? What are the differences? 뭐가 차이지? Only this one right here. Maximum likelihood and maximum. That's the only difference between maximum a posteriori and maximum likelihood. Okay? So how do you solve this? You take the derivative, right? But let's say the derivative does not give you a solution. Then how do you do it? That's EM. So I'm going to go by example. EM can be used in many, many situations. Okay? Many, many situations. So I'm going to take an example. I have two Gaussians. And they have different mean and variance. You can see that the means are different. The variance is going to be different. And they have different prior. What do I mean by prior? This one, the red one, happens with probability pi. The other one happens with probability 1 minus pi. So what is this? This is like doing this. I have two Gaussians, red and blue. I have a coin. Probability of head of this coin is pi. Tail is 1 minus pi. If the head shows up, I sample from the red one. If it's tails, then I get it from the blue one. You know what I mean? I might have switched those things too around. So tossing the coin, what is it? Oh, it's heads. So I sample from the red Gaussian. So it's a two-way process. How many parameters are associated with this? How many parameters? I have the mean, variance, and I have the probability of that one. Right? And the other one is 1 minus that. So how many is that? 1, 2, 3, 4, 5. That's theta that I need to find. Right? And I could write the Gaussian, this distribution, like this. Pi times the red Gaussian, 1 minus pi the blue Gaussian. Okay? And you can think of it this way. If it's with probability pi that I pick this one up, 1 minus pi is this one. So this is like this. I call the red one class 1. The blue one class 2. Class 1 probability I choose. Given it's class 1, I use class 1 parameters to get my x. Class 2 with this probability. If it's class 2, then I use that parameter, class 2 parameter, to get x. So what is this? If I do this, if I combine this, it's probability of what? Probability of class 2 and data. This one is what? It's probability of class 1 data. So when I sum up, what do I get? I've exhausted my classes. So when I sum up, what do I get? Probability of data. You understand what I'm saying? Okay. I would like you, in your head, quickly take the derivative of this and set it equal to 0. You think you will get parameter and the other side, the observation? No. So the likelihood is It's like this. And you try to do it, taking the derivative is very ugly. Okay? And I should say, okay, now this. Of course, I can do a graph on this. How do I draw a graph on this one? How do I draw a graph on this one? Now you should be thinking about graph. It's the class given data. Like that. And I think you have to also include the theta with this. Okay. So this is probability of C. You could take 1. This is probability of X given C. Right. So let's look at two-dimensional case. Okay. I want to show you why one is more difficult than the other. So I have data. Oh, tossing the coin, and then, oh, it's red one, oh, it's blue one, and from that I get two-dimensional data. The red one here and the blue one here, by doing that. And this is a distribution I get. How would I get the mean? How would I get the parameters from this one? Just tell me. It's easy. If I know which Gaussian. So this one came from the first Gaussian, class 1. This one came from class 2 Gaussian, right? So what is the mean of this one? The mean of the Gaussian. What is this? How would I estimate it? Throw away all the blue ones and just keep the red ones and take the mean. What about the covariance? Very easy. Just look at this and get the covariance of this one, right? What's one way? It's a vector. You take the outer dot product, and then you sum up all the outer dot products, and then you take the average. That's the covariance. And you could do that for the blue one, right? And how would you get the pi? Hmm? Yes. Of all the numbers, how many of all the data, what's the portion of the red ones? That's how you get pi. That's the maximum likelihood estimate. That's maximum likelihood estimate. Under the condition, what? That you know which Gaussian it came from. It's easy. But let's say you're given this situation. How would you do that? You don't know. You're given just the data. You don't know where the Gaussians came from. How would you do it? 어떻게? 모르지. 안 배웠어. Okay? So, in EM, I sort of mentioned this in my makeup class. For each of the data, so what I'm going to do is I'm going to initialize the pi, all the parameters, theta, initialize. Based on that theta, what I can get is I can get the, so what was important here to make this problem easy? In order to make this problem easy like that one, what do I need? Hmm? Yes, I need to know the color. Hmm? But let's assume theta. Just guess. What would I get? I can get for each one of them the probability of C equal 1 and probability C equals 2 for each one of them. So for all the data that I have, each one can be coming from red and it can be coming from blue. And then, what do? I say, every one of them can be coming. So let's say I want to get the mean of red. So I say, oh, everyone come out, because they all can be red. But each of them will have a different weight of being red because of your choice of theta. 뭔 말인지 알겠어? Because of your theta, each one will have a different probability of being red. So what I can do, in order to get the mean of the red, I could do a weighted average of each of them to get the red one. And weighted average to get the parameters of the blue one. Once I have that, then I can update my theta based on this. And then I do that procedure over and over again. So here, the lesson here is the latent variable C is not observed. Latent, it's hidden. So what do? This is in all machine learning algorithms. You don't see the good information. So you initialize and you give it some probability of being in all the situations. All the situations. And then you calculate. And then you update. And then you do this thing over and over again. Okay? That is EM. Okay? So finding out the average is the expectation step. And based on that average or the Q function, maximizing that process, updating the process is maximization. So that's expectation maximization. Okay, we'll go through the math. So here, if you know the color, if I knew what the classes were, then it's very easy. Okay, and that's what I've said here. And this is the algorithm, EM. You initialize to something. And what have I done? Initialize to something. Based on that initial parameter, I have the data. So what am I calculating? Probability of the class. Probability of the latent variable. Okay? Which means that each one of the data point can be either red or blue. And you will see this thing in many situations. You have a very difficult problem, and I wish I had the label for that one. I don't know. So I consider all the situations. Okay? And I give it some probability. Based on that, I can calculate. So this is called the expectation step. Expectation. What's the probability of red or not? That's expectation. The maximization. Oh, I consider the data with the vital latent information. What is the vital information in this case? It's the color. I consider it with all the different colors. But the colors happen with what probability? With that probability. And I take the average. And I want to find out the theta for this one that maximizes it. That's the maximization step. And I repeat. So this is actually an example that's given in the book. So this is Yellowstone Park. And there is hot spring that's coming up. Okay? It's erupting. And it's erupting. Here is the distribution of duration of eruption and time between eruption. Okay? So when you go there, it's not erupting. You cannot see it right away. It's following this type of distribution. Okay, so here it's erupting for maybe 2 minutes. But the time interval for that is, what is it? 45 minutes. You have to wait 45 minutes to see the 2-minute eruption. Well, if you want to see like a 6-minute eruption, which happens very infrequently, you have to wait 100 minutes. So when I went there a long time ago, I didn't know machine learning. But now I know machine learning, and this is the data that I have. So this looks like what? How is this thing distributed? Maybe there is 2 Gaussians here. So I'm going to model this with 2 Gaussians. So my initial guess was that 2 Gaussians, the mean here and the mean there, and the variance to be equal, unit variance, 2-dimensional. This is my initial guess. Then I do an expectation. Based on this, what is the probability that this one came from the red one and the other one came from the blue one? Here is the plot of the expectation. And you see the ink. The proportion of the ink, the red ink and blue ink, tells you what is the probability that it's associated with one. Then, based on this is new data on the red one and new data on the blue one. I can update my mean variance. And here it is. I do it for 2 times, 5 times, 20 times. EM algorithm. So what is the issue here? So we all know the philosophy. The important thing is the understanding the philosophy. So details. How do you initialize? Some initialization gives you fast convergence. This is what most people do. Choose data at random and use that for the mean. Okay? Choose that. And for the variance, you choose the variance of the whole data over all the samples. Okay? And pi, you usually choose as half and half. So I've said everything. So let's look at math a little bit. Okay. So I'm going to call this gamma I as the probability of this. So it's good to go through this exercise. This is the probability of the latent variable given the parameter and the data. And CI is the label associated with data xi. Each data is associated with different latent variable, right? Do that. So now we do some manipulation. You should be able to do this right away. This is easier to consider than, rather than this one, it's easier to consider that this is true. And what is this probability? What is this probability? It's class 1, and you have theta and data. So you look at the probability of what is this? It's, yes. So this is class 1, the probability of class 1, that's pi, right? Let me just do this so that you understand what I'm doing. Okay, here. Class 1, which one is that? If it's class 1 in data, then it's coming from there. What about probability of data? That is coming either from class 1 or either coming from class 2. Right? 1 minus gamma I will be the probability of class 2, given all that, right? So it's that. And similarly, you can do this. Not too difficult, very easy. Okay? Maximization. So now I have to do this. What is maximization? Maximization of the expectation. By the way, I didn't mention this. There's a terminology that's used in expectation maximization. Here is the hidden label. Latent. That's the data. That's visible data. When you combine this, what do you call this, the whole thing? There is a word. Complete data. You know all the vital information. But of course, the latent data happens with this probability. Right? So how do you do the log of the likelihood of the complete? So this is the log likelihood of complete data. Right there. And you can write it like that. There it is. And the expectation is over that, so it's there. And expectation, you're doing expectation, so you do it over all. So this expectation expectation is over all there, right? No, expectation over all there and all data. Okay, so you know all this form. Okay, this is called the gamma. The log of that is that. Sorry about this. So I'll just do a green one. Green. That's the green. That's the green. Okay, and U1 would be that. And it turns out this. Is there a meaning to this solution? Is there a meaning to this? So it's all the data, there are n data. So this is what is this? This is the mean of the red one, right? Gamma I says the probability that xi is in class 1. Huh? Probability of class 1 of data xi. That's what it is. So xi is in class 1 with this weight. So I do a weighted average divided by the total weight. So that it's normalized. It's normalizing. Right? And you can get all the other ones. And gamma is, if I sum up and take the average of the gamma, what is that? This is the likelihood that each of the data is in class 1. I'm taking the average, that is pi. I have a little bit more time. So I want, any questions? Oh, there's some properties associated with EM. It's an iterative algorithm. You initialize, and then you update your parameter theta. Every time you update, the likelihood increases monotonically, meaning that it increases or stays the same. It never goes down. And you can prove that. And someone mentioned this. Many of the algorithms today are based on gradient descent. And I'll be don't have a section for this. So usually you do this. This is how you do the parameters are updated. This is gradient descent. This is is how most algorithms these days are updated. I have a loss function. I have my criterion. I take the derivative with respect to the parameter. So this one is in which direction? Is it increasing the loss or decreasing the loss? The gradient. Which way is it? This is increasing loss. So let's say I had a parameter at time t. Okay, this is an iterative algorithm. At time t, I go in the opposite direction in the theta space to the gradient. So what is that going to do? If I do this, it's going to lower the loss function. What is eta? It's the learning rate. We call it the learning rate. And there are some others. So this is what a lot of people do these days. Gradient descent. But this EM, if you can do EM, it's easier than that. But sometimes slower at the plateau. What does that mean? When you're very near the optimum, then it can be slow. Okay? So I want to do, I have about 5 minutes left. So I do this so that I can give you an exam problem related to this mathematics. Okay, let's say I have a current model theta, and we like to find an updated model theta hat, okay, such that the loss becomes smaller. This is the loss based on the current, and this is the updated. And when I subtract, this is greater or equal to 0. So this means that this is smaller than that one, right? Theta has been updated, and it has made the loss smaller. Okay? And we want this to happen. Now, observe this. H is C. H stands for hidden. Okay, in general. In the Gaussian, oh, by the way, another word that I need to mention. This by the way, has a name. It's called Gaussian mixture model, or sometimes GMM. With how many mixtures? With two mixture GMM. Okay? Is GMM an exponential family? No. GMM is not. It's a lot of people use this two mixture GMM, but this is not in the exponential family. Okay. Want to make that? Okay. This is in general. We have 3 minutes to do this. Okay, so hidden. Here it is. This is the class. Obviously, I can do this. Okay? It's just using Bayes' rule. And so I could switch that, and I could do this. right? So switch that with that. Then I take log on both sides. Log here, okay? Which is the log, what is this? Of that, right? If I take this, get to subtract that one to that one. What is this? What is the probability of what is that? What do we call this? H and D together. Complete data. Okay? That's the likelihood of the complete data. Subtract the hidden. That's this. And I could take the expectation over the hidden. And I call this the Q function, and I call this the R function. And it turns out this R function is always positive. I don't need to worry. I should just focus on maximizing the Q function. And I'll talk about this just a little bit later next time. Okay? It's 2:14. I don't think I can finish this. Okay, so I do this today. So I'm finished with EM. And maybe I'll talk about regression next time. And so it's EM and regression and maybe a little bit of graph model in your homework. Maybe three problems before the exam, which is on Tuesday. Okay? Okay. I'll see you Thursday.